Radiation. Electromagnetic radiation, energy in the form of electromagnetic waves or protons. Non-ionizing thermal radiation. Radio waves. Radar. Microwave radiation as used in microwave ovens. Visible light. Light that is visible to the naked eye. Ionizing. Ultraviolet radiation is electromagnetic radiation with a wavelength shorter than that of visible light but longer than soft X-rays. X-rays used in radiography for medical diagnosis. Gamma radiation, usually emitted by radioactive atoms. Particle radiation, energy in the form of moving subatomic particles. Beta radiation, consisting of energetic electrons or positrons. Neutron radiation, consisting of neutrons. Effects of electromagnetic fields. Positively charged alpha particles are deflected by both magnetic and electric fields. Negatively charged beta particles are also deflected by both types of fields, but in the opposite direction from alpha particles. Neutrons and electromagnetic radiation have no charge and consequently are unaffected by electromagnetic fields. Time. The amount of radiation exposure increases and decreases with the time people spend near the source of radiation. In general, we think of the exposure time as how long a person is near radioactive material. It's easy to understand how to minimize the time for external, direct exposure. Gamma and X-rays are the primary concern of external exposure. However, if radioactive material gets inside your body, you can move away from it. You have to wait until it decays or until your body can eliminate it. When this happens, the biological half-life of the radionuclide controls the time of exposure. Biological half-life is the amount of time it takes the body to eliminate one half of the radionuclide initially presents. Alpha and beta particles are the main concern for internal exposure. Distance. The farther away people are from a radiation source, the less their exposure. How close to a source of radiation can be without getting a high exposure. It depends on the energy of the radiation and the size of the source. Distance is a prime concern when dealing with gamma rays because they can travel long distance. Alpha and beta particles don't have enough energy to travel very far. As a rule, if you double the distance, you reduce the exposure by a factor of hour. Having the distance increase the exposure by a factor of 4. Shielding. The greater the shielding around the radiation source, the smaller the exposure. Shielding supply means having something that will absorb radiation between you and the source of the radiation. The radiation doesn't count as shielding. The amount of shielding required to protect against different kinds of radiation depends on how much energy they have. Alpha. A thin piece of light material such as paper or even the dead cells in the outer layer of human skin provides adequate shielding because alpha particles can penetrate it. However, living tissue inside body offers no protection against inhaled or ingested alpha emitters. Beta. Additional covering, for example, heavy clothing is necessary to protect against beta emitters. Some beta particles can penetrate and burn the skin. Gamma. Thick, dense shielding such as lead is necessary to protect against gamma rays. The higher the energy of the gamma ray, the thicker the lead must be. X-rays pose a similar challenge, so X-ray technicians often give patients receiving medical or dental X-rays a lead apron to cover other parts of their body.